I'll get into some of these in a little bit more detail around some of the operations changes that are going to happen, that have been happening and are likely to start happening more in the future as well, the kind of things to be looking out for. Obviously, and Debbie covered a lot of this already, the why we're evolving these, the changes in the generation mix with wind and solar, batteries, potentially other resources into the future, longer duration storage and hydrogen and other things that could be coming into the system. The increased amount of things happening on distribution will impact up on how we balance the system, and then the customer side of it, increased amount of customer interaction and electrification. Well, all of those things could complicate or change how we're thinking about operations. They give us new opportunities, and we look at how we can take advantage of that. So I'm going to cover four main topics here. I'm actually going to start with kind of simulation tools, which maybe seems pretty dry, but the reason for that is we're trying to understand some of these changes into the future. The best way to do that is to study that. And that requires changes into how we actually study the future system operations and kind of come up with new ways of operating the system, or examine how new technologies can be operated, those types of things. So I'll briefly touch on that first. One of the key ones that's a way to use to better integrate these new resources is around forecasting. I'll talk a bit more about that, some of the ways you can consider risk in operations, and how you think through the use of forecasts in your operating practices. I'll talk a bit about ancillary services and some of the evolution that's happening there. They're a key enabler of increased amounts of variable resources, renewable resources, but also potential value stream for new types of technologies. So important aspect to understand in terms of the system. And then some of the other technologies, how we're using them, so some examples, kind of building on what some of the presentation that Debbie gave just now to talk about more about some of the new technologies. So that's kind of where I want to talk about. And same as with Debbie, put questions in chat while we're talking. When we think about variability and uncertainty, really the implications of renewables, the figure here is actually from the Irish system, where my accent is also from. It shows a week or so last summer in Ireland, with increasing levels of wind. Ireland had about 30% of its energy coming from, or 35% of its energy coming from wind that week, and over the year had about 30% of energy coming from wind, a very small amount of solar as well. Ireland has DC connections to the UK, but not anything else, and so most of it has to be balanced kind of on the island. So it has a lot of the same challenges you see in places like Hawaii, a slightly bigger system. So it does kind of show us what it might look like for other systems as they get more wind and solar there as well. What you can see there is a few different lines on the different axes. So the blue and the green are the load on the blue, the load. Or sorry, the demand is in the dashed blue line, the generation is in the solid blue line. The difference of those is basically the import and export to the UK. And then the green is the forecast of actual wind power. So you can see in the orange line shows how the instantaneous penetration, you can see the kind of challenges people will have to deal with, where early in the week you had pretty much zero generation from wind energy at that time. And then over the course of about a day and a half, it went from there up to 60% plus of total generation. So pretty significant amount of renewables coming online over that period. You had to back other generation down. The forecast helped. You can see the dash line and the green solid line are pretty close to each other. The big gap at the end there is because they actually have to curtail renewables once they get to a certain percentage of instantaneous penetration. They have stability concerns that I think will be discussed more in next week's or the next training session around stability. So they do have these limits on how much they can currently accept, and they continually push those up. There was 65% last year, now it's 70% of instantaneous renewables. So that's kind of where the variability, these are the types of challenges people are having to deal with. They're having to forecast it. They need to manage the kind of ripple, the smaller effects that are happening within the hour, but also then the kind of larger ramps across the day. And so a lot of the things Debbie talked about, the scheduling and reserves and other topics, become more important. So you have to think about what reserve you're carrying, match it to the amount that's actually needed. understanding how much distributed resource is out there and masking that and making sure you got the stability on the system. Things like outage scheduling become more complex. If you don't know exactly how much the wind is going to be in the next week or two, you have to think about when it's the best time to take outages on conventional generation or transmission to do maintenance. You see changing flows across the system. So power transmission networks that were built for flows in certain ways at certain times. That's changing now on a more regular basis. So that challenges a lot of the way we operate the system. So then we do need to kind of simulate a lot of this ahead of time so that we can study that, make changes, make improvements. And so the simulation tools have traditionally been more about the economics or having to start to think about some of the technical aspects as well, capturing things like the high resolution in terms of time or space so that we can better understand how uncertainty impacts the system and how variability impacts the system. So that's really what we're looking at in terms of the types of things you're trying to manage now and the types of things you're trying to study for the future. The uncertainty aspects, when we look at that, there's kind of uncertainty, and Debbie talked about this already, how as you get closer to real time, you have more certainty about what might happen. As you go out a day ahead of time, you're starting to see wider range of uncertainty. And you've also though got different actions you can take in the shorter time frame. There's only smaller amount of actions. In the longer time frame, you have more actions. So as Debbie said, there's a lot of need to kind of use the forecasts that are close to real time, while at the further out, kind of making sure that you can cover the various scenarios that are likely to happen. So when we look at kind of operational simulation tools, one of the things we've been working a lot on in the industry over the past few years is better models to actually capture when and how you take decisions, so you can really inform that decision-making process into the future. So this gives an example that the security constrained dispatch that Debbie was talking about, or unit commitment, where you're deciding whether or not to turn on a unit. That happens in a day ahead basis, looking at the next 24 or 36, 48 hours. You look at it on an hourly basis, but then as you get closer to real time, you start using more high resolution models, 15-minute or eventually 5-minute in your real time dispatch. So being able to do that in a simulation allows you to actually play out what the day would look like with higher levels of renewables or with other changes to the resource mix. So having that 5-minute type modeling. Traditionally, we've done these types of models in a zonal way, where you look at the entire system as one big area. Being able to actually look at where the transmission is and how to consider the transmission is becoming more important. Multi-cycle, the figure here shows the kind of capturing the different decision-making cycles and being able to do that in a simulation. And then things like storage and how you interact with neighboring systems. There's a lot of capabilities that are now starting to pop up. Through a lot of the integration studies, you saw the results that Debbie was showing in her presentation about different integration studies. They've kind of led us to improving the tools here, so we can now really study some of these issues in more detail. And I'll talk about the implications of that in the rest of the presentation. There are some things, just get through this pretty quick. There are some things that are still needed in terms of evaluating the benefits of a better forecast. A lot of the tools, it can be hard to always quantify what the benefits of improving your renewable forecast might be. The benefits of things like a longer look ahead in your dispatch decision or your commitment decision. So instead of just once a day looking for the next day or the next 2 days, you might look out a week ahead of time. Quantifying the benefits of some of those and being able to look at that as we get more renewables and we need to shift energy across days, weeks, or even seasons. We're going to need to start thinking about operating tools that actually can help us with that. New ancillary services, touched upon the kind of need for stability, and that might result in things like inertia being valued as an ancillary service. So the tools that we use need to be able to reflect that and show the value of those types of resources or those types of services and the provision of those services from different resources. Gas pipeline, I'll talk a little bit at the end here about some of the work that's ongoing in the industry and that, but increasingly we saw this in Texas in February, but even in less extreme cases, you see the need for better representation of the gas network in the market models and vice versa. And so coordinating that both in the study timeframe and in the actual operations timeframe becomes important. Storage, demand response, those types of things, they don't behave the same way as a traditional coal or gas plant. And so we need to be able to model those in our market models and dispatch tools, as well as in the study tools, so that we understand what their value is and how we can go about procuring those types of resources. So understanding the value of different shades of demand response to the system. So if it's a different type of technologies or different type of demand response programs, each of them will have their own strengths and costs and benefits, and being able to study and simulate those becomes increasingly important. And then there's things I'll talk about in a while around new scheduling techniques, the interaction with the distribution system. And obviously all of this is coming as we evolve the electricity markets, as we evolve the way we operate the system. And so being able to reflect some of those changes as we make those in time becomes increasingly important. So they're the kind of things that we'd be looking at in terms of new changes to the system. So we'll talk a bit more about that in the rest of the presentation. Just real quick, when we think about flexibility and operational flexibility, we had a pretty good lesson that we learned last year during some of the COVID periods. As folks will be aware, the demand for electricity declined in most regions there. A lot of the decline was related to the severity of shutdowns. But we did see in places like California, and certainly in places like the UK, where they have a lot of wind and solar already, flexibility challenges in their operations. So they had an opportunity, or they were forced into the need to see what would it look like. Maybe they hadn't been thinking some of these issues were going to happen for a few more years yet, but because the demand reduced, but the load was higher, but the renewables stayed at the same level, you got these high renewable, low load type days last spring, maybe earlier in the planning process, earlier in the process than we would have expected. So there was a lot of work there done in places like the UK to better respond to those low load, high renewable conditions. So having signals sent out to distributed resources. So similar to the comment, there really isn't any control until recently for distributed resources on things like distributed solar. But they did start actually accessing some of the flexibility. So going out from the transmission system operator to the distribution network operators, sending signals to curtail renewables. That capability was put in place. They didn't really need to use it a whole lot in the UK, but they did start putting that capability. So they had the ability to do that, and then looked at other markets as well to be able to increase the flexibility to the system. So sometimes with some of these events on the system, we end up learning lessons and doing things quicker than maybe we would have otherwise expected, particularly in this case around the flexibility issues. And there's more detail on this paper that you can. There's a link if you just click on the figure once you get the slides. So that's kind of just general context of why we want to look at these things. We're trying to study what's the flexibility needed now in the next day, the next few months, the next hour, but also if we're looking into the future, how we actually understand how the system may operate so we can make better investment decisions that reflect the real operations of the system. I want to dive into renewables and load forecasting a little bit more here for the next few minutes and talk a little bit more about build on what Debbie said. I think Mark may have some material on this as well later, but in terms of forecasting, how the transmission system, the bulk system uses forecasts generally, everything from years ahead down through the kind of real time, there's use cases of forecasting. And the years ahead, you're thinking about the climatological forecast and using that to understand where the system might go in terms of demand, in terms of renewable output and expected renewables. Big piece of that obviously now is starting to consider climate change variables in there and understand how that's going to impact on the resource mix going forward. Other things as well, we use it for the production cost modeling, the simulation tools I mentioned in the previous section, being able to look at those and using meteorological data there. Then as we get into kind of the year ahead and season ahead, you're looking at whether you connect generators, hedging fuel, optimizing your fuel usage, maintenance on assets, and making sure you got the reserves and services that you need in that kind of year ahead to season ahead time frame. And then a lot of it's around this balancing area, the scheduling, congestion management down into real time. And so that comes a lot from forecast providers. There's a lot of commercial providers out there providing these types of forecasts to utilities and system operators. Some of them also develop their own in-house, and a lot of them they're all based on the government weather models that we're all familiar with from just the normal weather forecasts. And so a lot of those are now being specialized to be able to better use or better forecast things like solar output or cloud cover, wind speed, and other factors there. Debbie already mentioned this can kind of improve the visibility. And there has been a lot of improvements in recent years. You don't really see it that well here in the bottom right. There's a link for more information. But we did an evaluation a few years ago of forecasting performance that I'll talk about a little bit more in a while. But did see for solar forecasts that there's a variety of different commercial providers, and there is a variety among their performance. Some of the best ones have a 5% average error. That sounds pretty good. I'll talk in a while about the kind of extremes on that, though, and why that's important to think about. But there are different ways to do this forecast. You can see on the top right some of the different methods for say solar forecasting. On the nearer term, the satellites that are out there, the high resolution satellites that have been put up would be very helpful for forecasting cloud cover. On the even shorter time frame, putting cameras up on solar panels or solar plants will help there. That's less useful for wind, but other types of sensors and data that you can get directly from the wind plant can be helpful. And then going out into longer time frames, it is the computational methods where you're using the weather forecasting systems run by national labs, sometimes downscaled by commercial vendors, but they start assessing the ability to assist or the expected changes. And then out into the weeks and months is where you start thinking of just kind of regular climatology. But when that gets mixed with other aspects, you can kind of do the overall forecast. This is kind of overall how the system works. That those computational models are up in the top left. Sometimes vendors will have their own models they build on top of those. They'll certainly be using statistical and machine learning methods with data from the wind plants or other weather data. And together with that, they'll be able to produce a kind of a power forecast for renewables. A lot of the same information is used in our load forecasting, though typically our load forecasting tools have been pretty well performing, because whereas in power and in wind and solar, weather is more of is the prime variable that actually drives whether there's going to be wind power output or solar output. With load, it's more it modulates the expected underlying activity that we have anyway. So weather forecasts, while important, are not quite as important on the load side as they would be on the renewable side. And then thinking about the different ways you can actually classify a forecast. So forecasts come in all of these types of products. So minutes ahead, it's going to be important to be able to understand if there's going to be a large ramp in the wind power output or solar power output. That'll be unexpected. The day ahead is really around that scheduling time frame that Debbie was mentioning, which generators to turn on or off, which ones are going to carry reserves, what's the way you might need to go and buy gas from the gas system or store energy to make sure it's there later on in the day, those types of things. And then days to weeks ahead, where you're starting to schedule longer start units, some of the existing coal plants, nuclear plants, other things that take a while to start up and shut down, as well as kind of gas purchases, maybe longer duration storage, pumped hydro, that type of thing, where you need to look over multiple days or weeks. You have different levels of forecast for something like a system operator. You're probably more interested in the overall system, the overall wind in a given region, whereas some of the power plant developers or some of the folks doing trading might be more interested at the plant level. And then if you're looking at maintenance and other things, you might look at the turbine. You can use historical only information, though typically that's not common. Most people will use one of these numerical weather prediction tools to support their forecast. And then we've already kind of touched on some of these where the different types of models. Persistence at the very short term, just assuming it's going to stay the same, or for solar, assuming that the cloud cover is going to stay the same, works pretty well up to about 5 or 10 minutes out. Beyond that, then you start needing statistical models or physical models and combinations thereof. I'll talk a little bit in a while about the different forms of forecast, but basically, not just that. Typically, when we get a forecast, it's kind of a best guess of what's going to happen an hour from now or a day from now. But we also have other types of forecasts, probabilistic ones, where you're giving a spread that I'll show later, or event-based, where it's telling you the likelihood of a certain event happening, a large ramp up or ramp down in wind power output, for example. So these are different types of forecasts, and they are used in a lot of different, or they're used now in all of the system operators all have some form of centralized wind and solar forecasting, and most of the regions outside the ISO RTO regions are also using something related to wind and solar forecasting, as well as traders and participants in the markets are also then using those. There's multiple applications they use, as I talked about. The ramp forecasts are getting some interest, and some folks are using those. Cost allocation of forecast is quite varied. Sometimes it's put directly on the wind and solar plants, sometimes it's socialized. That does encourage or incentivize different types of behavior in terms of how those are how the cost is put on people, how the cost of the actual forecast, as well as the cost of the uncertainty, in terms of being able to mitigate the uncertainty on the forecast. But right now, most things are deterministic. I'm talking a bit about probabilistic and the need to move to maybe a more risk-based operations, given the nature of the system and how it's changing. These are some examples of these from some of the commercial vendors. So these kind of best guess, you can kind of see the central line, or the kind of best guess forecast, but they often have bands of uncertainty around them as well, to give operators a sense of what might happen. So in certain hours, you're pretty sure what's going to happen. You know, a certain weather front's going to move in, but typically as that's moving in, you might have challenges. And then, as you can see in the top here, there's kind of potential periods when there's a higher risk of heavy ramps on say, in this case, a wind power output. The bottom one again shows kind of that idea of ramps, and being able to kind of give that awareness to operators, so they know that something might be coming over the next few hours or the next day that they need to be getting ready for. How these perform, I mentioned we did some work previously in Texas looking at this, and don't want to spend too long here. Each of the colors is a different forecaster. Each of the kind of groupings is a different solar plant. The concept here, though, is that there is a range of performance. Their mean absolute percent error. So that if they're a 100 megawatt plant and they have a 10% error, that means on average during daylight hours it's a 10 megawatt error. So that's kind of showing what the error might be expected. So operators then have to deal with this type of error, and I'll show in a while that's not evenly distributed across the day or across the year. At certain times of the day and year is when we see most errors. So when we're thinking about the value of a forecast and we're thinking about how to use them, one of the important pieces is understanding what the forecast can't do, and understanding the error in the forecast, so that then we can kind of operate around that and carry enough reserves and carry enough headroom in the system to be able to manage that forecast error. This is the same trial, but looking at this by time of day, and then this gets into a lot of detail, but basically the way to look at it is each of the colored bars is a different time of day, and from left to right within the bars is a different look ahead, so week ahead down through hour ahead for that hour of the day. Don't need to get into this in a lot of detail. The point of this is really to show that even though those errors end up being an average, that kind of 5, 6, up to 10% in some forecasters, there's certain times of the day and there's certain times of the year when you can get up to 40 or 50% errors. So the operator then has to be able to manage that in an economic way. So they should be trying to minimize the amount of renewable or reserves and try to use the renewables as best as possible. But at the same time, they have to be prepared for some of the larger errors to happen as well, and carry reserves or carry some way of doing that, allow for curtailment and other options to provide flexibility. That gets us into the kind of use of probabilistic forecasts. So not just best guess, but if you think about a hurricane forecast where you see the hurricane path, there's typically a wide amount of uncertainty days ahead. Similarly with renewables, you can get from a forecast provider, you can get that kind of path of where it might go over the next few hours or next few days. This gives some examples of how that might be displayed. On the top, you kind of got intervals to say we're 90% sure it's within this interval, or on the bottom, it's kind of got potential trajectories around where the output of that, in this case, wind resource might go. So being able to use those and apply those to system operations becomes quite important as we're integrating more amounts of solar. We and others, some of the national labs and others, are starting to look at using risk-based methods, so that we're not just operating based purely on the expected error and the expected wind or solar output, but taking into account some of this information when we make operating decisions, so that we can actually capture some of the more extreme events while still keeping it to be economically efficient. Because the other option would just be to always assume the extreme events likely to happen, which would be a very expensive way of operating the system. So again, using some of those simulation tools I talked about earlier on, actually running through those and capturing the benefits of using some of these newer techniques to operate the system in a more risk-based fashion. So that's where a lot of the forecasting is going. We'll continue to improve the forecasts themselves. We'll continue to get better at predicting output of renewables or load. But at the end of the day, there is a limit to how well you can forecast anything. given this is an inherently complex process. So being able to use some of these risk-based methods is going to be extremely helpful in terms of how we operate the system into the future. That then gets into kind of the ancillary services aspect. So even with the best forecasts and the best uses of them, you're still going to need to carry reserves, ancillary services, grid services, different kind of names for some of these. I'm going to go through these at a pretty high level. Some of these will actually be covered in more detail in the next talk on stability, particularly some of the ones on the top, in the middle there, the contingency reserves and some of the voltage stuff. But just to give a quick overview of kind of how these are done, what's covered in markets and what's not covered in markets, how these are going to be impacted by renewables. So typically on the operating reserve time frame, we're thinking there about a generator that's partly loaded, or maybe some demand response that's available to use to provide response based on either an event or just based on kind of steady state variation. So the terms can be different here. You go to a different system operator, you go certainly a different country, you would see different terms being used. But essentially what we're trying to do with reserves is respond to things that are happening on the system. So when we think about events, that's really the trip of a large generator on the system, and you can carry different types of reserves there up on the top right in gray, different contingency reserves that are used. Inertia is something that isn't really being used as an actual reserve right now, though there are parts of the world that are starting to pay generators to have inertia, because could be an important part of the system if we're not using other technologies that I think will be explored further in the future discussions. But other types of response then, that as you get further ahead in time or longer time durations, fast frequency response, then you got kind of primary reserves to stop the event happening, to stop the reduction in frequency, and then other things to kind of bring you back to where you were before the event happened. So various different categories of reserve. When you add renewables to the system, these contingency reserves, the sizing of them may not change significantly. What might change is the relative importance, for example, of some of the quicker responding stuff. When the system reduces its inertia, it responds quicker, and therefore you might need more fast acting resources on there. But the actual imbalance size itself is typically the same, if not smaller, because the renewable plants tend to be smaller than some of the larger generators right now. So that kind of contingency reserve will be impacted and talk more about in the stability aspects. Ramping reserve in this context here as a ramp to an event is typically not something that's captured in most systems right now, but this is where you might have a very large ramp of wind or solar, and having a specific reserve just to manage those could be something that's used in the future. The bottom two are really some of the ones that are most relevant for balancing, and Debbie's covered a lot of this already in the discussion around kind of keeping the vehicle on the road. But the regulating reserve is that quicker time scale response, where it's an automatic control. It's within the dispatch period, and you have some response there. That's likely to increase with renewables, because you do see additional variation, but the increase can be relatively small, especially when you look at larger regions. The following reserve then is a newer product in some regions that people have introduced. I think Mark's going to talk about it, but the idea of this kind of load following or flexibility type reserve to manage some of the longer duration, minute to minute or 10-minute to 10-minute type periods there. So these are the kinds of reserves that people are talking about carrying. For all of these in the middle here, it'll be important to dimension them properly, as we're getting more marginal costs, zero marginal cost resources on the system. Potentially the value of some of these resources these reserves might increase and be a particularly big value for certain types of resources. And then on the right, some of the stuff you would cover the planning reserve and the resource adequacy kind of a concept already, and the other ones I think will be covered in the stability discussion next week. So I'll kind of keep that pretty short. When it comes to ancillary services, though, there's different ways people have been thinking about this changing into the future. As we look at evolving markets, one of the potential outcomes, and we've started to see this in places like Ireland, is as a total portion of the overall system, energy costs are going down because the actual fuel is often free or lower cost. But things like capacity and ancillary services values are increasing. And so having that happen may change, or as you add more renewables to the system, you might change the relative mix of the energy markets. The kind of questions you're asking then are, some of these resources will still be needed, but for less periods. So how do we make sure they stick around and compensate them? How do we compensate flexibility and incentivize flexibility so that things like ramping are actually provided to the greatest extent possible? When we look at essential reliability services, these are the kind of frequency and voltage type issues. How do we actually incentivize those? What are the ways we're making sure we have sufficient amounts of those on the system? There's just a general question about what the right price is, price formation. It's not like one of my colleagues talks about, it's not like you stick a meter into the wall and you get a price. You can do that for voltage or frequency. For price for electricity, it's a construct based on specific equations that we're using. And so being able to understand what that right price is going to become important. I'll talk a bit in a while about the transmission and distribution interface and being ensuring that we're getting those resources from distribution that we need. And then, as we think about this, do we need to, how do we actually think about the changing resource mix? Do we want to go out and incentivize specific technologies or specific characteristics? Or do we want to stay technology agnostic? The markets are typically designed to be technology agnostic, and you'd want to keep it that way as much as possible. So trying to think through how you can do things in a way that's technology agnostic, while maintaining some degree of simplicity. I think that the idea there is you want to be as complex as you need to be, but no more complex than that. So they're the kind of questions that the market design folks are wrestling with. I don't want to spend too much time on that, given this is more focused on balancing, but that's kind of where we're at. And then when we think about kind of designing reserve needs, so I talked about the different types of reserves, but how much you actually need to carry on the system. We've broken it down into a few very specific types of reserve that aren't really reflective of the way we currently categorize reserves, but they're really trying to look at what the needs are. So if you think of a forecast, and this could be a net load, it could be wind, solar, but it's really what the system is trying to meet. So something like a net load, the load net of wind and solar over a 20-minute period. That might be what you forecasted on the system. This might be what happened on average in those intervals. And so you might need to be able to manage that type of uncertainty. So you have to be able to make sure in your operational planning process, you have enough reserve to manage the difference between what happened and what was planned. And then you also need to be able to move from one of those intervals to the next. You need to be able to have enough ramping capability on the system. And then of course, in reality, it's not flat blocks of energy every 5 minutes. It's something more variable. And so you need to be able to manage that variability within the interval. And that's where frequency regulation and other products come in. So being able to look at it this way allows us to break down the reserve requirements into what's actually needed. It's the interval variability, the interval uncertainty, the intra-interval variability, and the inter-interval variability. And once you think of it that way, you can actually classify most of the reserves in this way and then start quantifying what we need. So we've done a fair bit of work looking at this and trying to understand what are the types of reserves. The other part of it is, as Debbie mentioned, there are NERC standards. You have some tolerance. You don't have to meet this every single second of the day, but you want to be able to meet it some high 90s percentile or some fairly large amount of time. So that's kind of the reserve needs that you have. And then we've been looking at how do you actually calculate what those needs should be. So what we've done is do the classification I just mentioned, and then look over historical time periods, looking over a year or 2 years or 3 years, determining what would you have actually required for each of those reserve types if you had known everything. Obviously, you don't know everything, but if you had known everything, you could kind of look at what might have happened and then classify that. So you can start to say, well, during periods of high wind and low solar and certain times of the day, it turned out that to meet the worst case scenario under those conditions, you need to carry X amount of reserve. But during other conditions, you might have needed to carry a different amount. And so you don't always carry the worst case anymore. You carry the worst case based on the particular conditions that you're expecting on the system. And we look at this over different types of hours, seasons, the different changes in production, those types of things. So we do that and then kind of come up with what are the ways that we can best explain reserve requirements that gives us some kind of an equation. So basically what we're doing there is we're looking at forecasting this. We've applied this in a few places, but the most notable there was Hawaii. By being able to provide this type of reserve versus their existing process in Oahu, they were able to save millions of dollars in operating costs a year just by providing this type of reserve versus something that was a little bit more static and a little bit more based on kind of worst case events. So there's opportunity as we get more renewables on the system to operate a lot more efficiently and optimize a lot more the operations we have. And this shows the example in the Hawaii system. You can see kind of with their existing over here on the bottom, the kind of middle of the graph or the higher black line, they have more costs on the system, and then as they start using these additional methods, they can reduce the costs, while also if they look at the gray and orange bars, which kind of represent risk, they can reduce the risk in their operations as well. So you kind of see this cost reductions while improving the reliability. We're working on a DOE project to do some of this kind of stuff in the in other parts of the system as well, in California and in the southeast with Southern Company and Duke Energy. So looking at how you might actually use some of these risk-based methods in an operational context. I'll skip through some of that there, but that's kind of the general idea.
Another 5 minutes, just to let you know.
Okay. Let me skip into some of the other stuff then. TNT coordination is going to be important as we get more resources on the distribution side. What I'm trying to illustrate here, don't look at each of the specific categories, but we did an evaluation with a DOE funded project a few years ago, looking at distribution and transmission functions. This is in planning, but it's a very similar kind of concept in operations. You can see the colored lines show when you need to interact between T&D right now. So you might need to do some interaction between the adoption of DER and generation expansion. That's already done. But if you look to the right-hand side, you can see far more potential touch points and coordinations needed as you get more distributed resources on the system. So the point of this is there's significantly more data might need to be sent, particularly on the distribution side. And we've definitely been seeing this in FERC Order 2222 as it's been rolled out, that need to coordinate. As we think about that, we want to design this to have certain principles. So we want this kind of level playing field. You obviously don't want to have potential reliability or other types of harm on the system. You want to be able to use these to provide a flexibility to the system, to support system congestion. New market participants could be another principle in terms of how you might design this. And part of it is having that observability and being able to see what's actually happening. That's on top of the existing market efficiency and market reliability objectives that all the markets have. But by adding in DER, you're kind of having to add additional thoughts around how we design markets. This gives a little bit more example on kind of how we might be able to do this through different types of features. So I won't go through these in a lot of detail. Folks here might be familiar, for example, with 1547. So by putting grid codes in place, we can better use DER by something like the industry and market structures down a bit. By having some type of locational price for distribution, we might be able to access some of the DER that's out there. And FERC Order 2222, I'm sure folks are familiar with that. There's a lot of implications of that. I won't go through these in detail here, but a lot of potential impacts there in terms of how we actually go about this. There's implications for the RTO, there's implications for aggregators, implications for distribution utilities. Being able to make sure we do that while keeping those types of design principles in mind is going to be important. And then when you think about practices and challenges, I'll skip through some of these relatively quick from time perspective, but what we're really trying to do when it comes to kind of maintaining reliability, we developed this chart a few years ago. I will say it needs to be updated, particularly some of the right-hand side of the chart, I think should be updated at this point. It's from 2015. But the idea was to kind of illustrate different types of services and who provides them right now, or who could provide them. In the case of yellow, it's those resources that could, even though they don't necessarily provide right now. But the idea is all these different types of stability stuff that's going to be covered next week, as well as the availability and ramping and reserves that I talked about today. So we do see that obviously as we kind of move from this synchronous based system to a system with a lot more inverters, we're starting to use these types of resources in ways that until now we haven't really used them to provide some of these services. And also looking at demand and trying to understand how demand can help with this. So we continue to update this, or we will update this in the next few years to better reflect the current state of the art, but it does give kind of the idea of how these different services can be provided. And just to give some examples then over the next few slides. So renewables, this is a dispatchable renewables kind of idea from First Solar, where they're looking at how to, and in California ISO, where they're looking at using smart inverter kind of functionality or inverter functionality to provide different types of services to the system. You can kind of see there's they respond to signals on the system. they provide you some headroom, they can provide reserves. If you add storage to the system, you can provide even more flexibility. And so being able to look at kind of using the plant level controls first to be able to dispatch the plant, and then actually adding storage to kind of firm up some of the capacity. Nuclear plants have operated flexibly in the past and could potentially operate flexibly again. Obviously, there's economic implications. Like nuclear production cost is very cheap, so you don't want to be moving it around too much. But at the same time, it has that capability. So understanding what those are able to do is going to be important. Hydrogen is going to be increasingly relevant and important. The example here on the right is from Germany, where they're looking across seasons, and you might need to shift it across seasons. But you could also use hydrogen to provide some of the other services. If you're using electrolyzers, for example, could potentially provide grid services. And so being able to do some of that can hopefully maintain some of the same existing characteristics, existing performance on the system, while being able to decarbonize. And then gas electric was another one mentioned. This is an example from a previous EC presentation given by some folks in the Northeast, looking at how the current system kind of is not got a whole lot of coordination, and that locks in some of the flexibility that might otherwise be available to gas plants because of the way that the gas markets are run. Being able to better coordinate it, like on the bottom, so they added in this case, they added in a conceptual balancing market. By being able to do that, you could potentially open up more flexibility to the system, and they've been showing this in some of the study work they've been doing. So that's kind of overall the various topics we wanted to cover, kind of following up from Debbie, looking at how we used advanced study tools, looking at things like forecasting and ancillary services, and how we might be able to use some of these newer technologies to provide some of that flexibility that we're now, that is currently being provided from kind of fossil generation. So that's kind of the end of my presentation, Debbie.
Okay, thank you so much, Aidan, for that comprehensive look at where things are going. So we got some questions in the chat. So Bryce Freeman asks, when you talk about inertia, are you talking about physical inertia like spinning mass, or are you talking about synthetic inertia?
Good question, and I'm sure some of the others will be talking about this in the stability piece much more. But I think if I'm remembering back to the context of the slide I would have had it in, it probably was in the context of spinning mass. So there's a lot of work now being done to understand to what extent and how do we use inverter-based resources to provide the same services. And then in some ways, then it becomes a matter of semantics. Do we call that synthetic inertia? Do we call it very fast frequency response or something else? I know in certain parts of the world, they've said, well, inertia has to come from a spinning mass, but inverters can provide fast frequency response, and we can substitute one for the other. So it depends really on how you think about it. The inertia from a frequency response perspective is really around slowing down the rate of change of frequency, and it's something that comes naturally from conventional generation, from spinning generation. But as you add renewables, they can potentially quickly respond to kind of synthetic inertia that you're talking about. So I think there's what really matters at the end of the day is overall system performance and how we get that. So hopefully it's a mix of the two, but in the end, it's the actual inertia, I think that was in that slide was referring to physical inertia.
Oh, thanks. And Blair Fink asks, if the utility doesn't supply inertia, will the customer be responsible to create it on their own? Like, would we have a possible inertia market in the future?
Yeah, I mean, certainly in terms of inertia markets, that's something being discussed. Right now, the way people have been looking at this is kind of there's an evolution from, and again, I think this will be discussed by folks more in the next one, but if inertia starts becoming a concern, the way it's being addressed in many regions right now is some kind of an inertia floor or a minimum level of inertia or a minimum level of synchronous generation. I mentioned Ireland having a 70%, a lot of that's inertia driven. As that floor becomes binding more frequently and you're having to keep generation online and pay it to stay online, there becomes a value in putting a market in that. The UK has a market now where they've been paying folks for inertia. And so yeah, that is likely to happen. The system operator will need to make sure they have sufficient amount of inertia. They will have obligations and will have to do study work to do that. And then, and based on that, they'll look at procuring something. So a market may be the best way to do it. It might not be the only way to do it, but it's certainly one way to think about it. And then that gets back to the other discussion around synthetic inertia and use of inverter-based resources. Certainly part of that should allow those to qualify for certain services if it makes sense to do so. And so the inertia concept certainly will be important. The ones I've seen that have markets for inertia right now, the UK procured inertia-based services back last year and did pay a fairly significant amount to a smaller number of generators to have inertia. The Irish system has a service now called synchronous inertial response, where they're paying generation, but it's not a whole lot. It's compared to other ancillary services or compared to energy or capacity, it's a very small amount. So it's not clear that that's the way it's going to evolve everywhere. Some places might see just a sufficient amount as they're getting other types of services online, but some places may have to go out and procure inertia.
Great.